Swayam Prabha. Digital India. Educated India.
Hi, welcome back to Mechanics and Control of Robotic Manipulator. So far what we have seen is kinematic model, especially we call geometrical model, in the sense the position model of, you can say, robotic manipulator, especially serial manipulator we have seen. This week onwards we are going to see differential kinematics, what that means. So one step further, so we would be seeing everything in the time derivative of the position, in the sense velocity model we are trying to see. So before going to see the velocity model, we will see what is the basic principle behind this. So what are the types of differential kinematics, and in that what matrix we end up. Although in the last class we have seen Jacobian matrix, we will be seeing the Jacobian matrix in detail, and then we would be actually like seeing how the Jacobian matrix can be used as a useful tool. So that is the whole idea in this particular lecture. So in the sense we can actually like see, we are going to talk about forward and inverse differential kinematics. These are the two types, and then we would be seeing that the inverse differential kinematics would be end up with the Jacobian inverse. So there we need actually like, if it is a rectangular, we may require actually like pseudo inverse. So we would be talking about pseudo inverse in the second half. The first half is actually like very straightforward. So we know the forward kinematic model as mu equal to function of q. So where q is a vector which would be a function of, or you can say vector consists of theta 1 to dn, in the sense, so it would be a rotary joint or a translation joint. So then theta 1 or d1 would be there. For example, I have so RRP, so then theta 1, theta 2 and d3 would be the variable. If I have RRR, so PR, then it would be theta 1, theta 2, then d3 and theta 4. Like that I would be having a vector. So this is what you call q vector, right. So if it is actually like 4 variable, then you can actually like see 4 variable you can control, in the sense mu would be, you can write as, so x, y, z. So alpha, beta, gamma would be what you call the 3 angular orientation, that is what we have written. But if it is in a plane, so if it is in a planar manipulator, these two, like a z would not be coming and these two also would not be coming. In the sense the mu vector would be reduced to x, y and gamma, right. So like that you can actually get, this is very straightforward, you recall. So whatever we have seen so far as a serial manipulator, these all forward kinematic solution we have obtained. But if you differentiate this with respect to time, so what you are trying to do, you are actually like having a mu as a vector, and this is actually like function of, so q is another vector, okay. So now I am just giving an idea. So y is actually like 4x plus 5x square, okay, where x is actually like, you can say, so probably 10t squared plus 5t minus 2, okay. So now if the equation is like this, so what you can see, y also function of t, but it is function of x and t. So x is actually like function of t. So in the sense I want to actually like differentiate y with respect to x, but differentiation in the sense a time differentiation. So then what I wanted dy by dx, okay, this I cannot do it. What I can do, so dou y by dou x into, I can actually like write this way. So what I can write, so dy I can take it by dt, okay. So which would give dou y by dou t, sorry, dou x, and multiply with dx by, so dt. So in the sense, so that is what we are trying to do. So in the sense I actually wanted actually like dy by dx, but I cannot do it. What I can do, you can see this dt all go away in principle. So the dou y by dou x is equivalent, right. So that is what we are actually like trying to see. The sense this is actually like by dt and this is also by dt, that is the meaning. In the sense here what you can see, So the dy by dt can be written as, first I will say that this 4, so dou x by dou t, so in the sense, so 4 into x, then x dot, okay. So this would be actually like 5 into 2x into x dot, right. So in the sense what you can actually like see it, so this is 4x dot plus you can write 5, so 10, right, 5 into 2, so 10x x dot. So this is the value will come. So now you can see what is x dot. So x dot is nothing but dx by dt. So what that value here, so it would be actually like a 20t plus 5. So now I substitute that here, okay. So then I can actually get it. So this is actually like if it is a scalar, you can do it. But now, so mu is a vector and q also a vector, in the sense mu is actually like n cross 1, okay, and f of q, where this q is actually like m cross 1. So now what you are actually like interested, you are interested is d mu by dq. It is not straightforward. So for that the Jacobi has given a method. So what that is actually like mapping two space, okay. So this is actually like mu space and this is q space. So where mu dot and q dot relation we are actually like mapping between one to another, either this or this. So this mapping, what we call kinematic transformation matrix, this matrix in the velocity form, this is what you call Jacobian matrix. So that is what we are actually like written. So very simple example, again I am actually like doing it. So for example, x is actually like L1, so cos theta 1, okay. So y is actually like L1 sin theta 1, in the sense it is actually like simple pendulum kind of thing, okay, where L1 is constant. So what would be this? So I can write x and y as mu. So in the sense this is 2 cross 1, okay. So where q is actually like only theta 1, which is 1 cross 1. What I wanted actually like, so dou mu by dou q, in the sense I can actually like write this. So I will write x dot, which is nothing but dx by dt, which is L1 minus sin theta 1 and theta 1 dot, right. So dy by dt, which is I call y dot, dot means a differentiation, right. So cos theta 1 and theta 1 dot, right. So if I take a partial derivative, what it will come? So it would come actually like, so this minus L1 sin theta 1, so this will come, so L1 cos theta 1, right. So now you can see these two are same, right. So in the sense, so x dot y dot, you take it one side. So what you can see, so L1 minus L1 sin theta 1, then L1 cos theta 1, so this whole multiply with theta 1 dot. So what is this? This is nothing but q dot. What is this? This is nothing but mu dot. What is this? This is a matrix. In this case it is so simple 2 cross 1, but what this? So this is actually like a Jacobian matrix, right. So this is J of q. So in the sense what you can see, the mu dot I can write as J of q into, so q dot. So this is the way we can actually like relate. So now this you can actually see, this is a partial differentiation of mu with respect to q, and this you can write mu dot divided by q dot, right. So the same thing what we are actually like writing in the other form. So differentiating with respect to you can say time, differentiating the equation with respect to time, you can see the mu dot we have obtained as J of q into q dot, where this J of q is actually like matrix of, you can say, partial derivative. Why it is called a matrix? So you can actually like rewrite this equation again. So x is actually like L1 C1 plus L2 C1 2. So y is actually like L1 S1 plus L2 S1 2. So if you actually like differentiate this with respect to time, you can see x dot y dot will come, okay. The other side it would be 2 cross 2 multiply with, you can say, theta 1 dot and theta 2 dot, right. So this is what you call Jacobian matrix, that is a partial differentiation. How you can write a partial differentiation? You can write dou mu, you can say I divided by dou q j. Okay, so where you can actually like write this would be, so dou mu I, where I can start with 1, so this goes till dou q j. So the second row like it is dou mu 2, which goes like this, and the final one is dou mu I goes to dou mu I, so q1 to dou qj. So what this means, I goes 1 to n, j goes 1 to m. Okay, so this would be m cross 1, that is what we have said, this is n cross 1. Okay, so some book would have written this is m, that is n, so you can actually like write it that. Okay, so that is a uniform format. Then this would be m cross n as the size. Okay, so now this is what you call differential kinematics. Now if I know the q dot, I try to find out actually like j of q. If the q I and q dot of I are known, what I can find? I can find the mu dot. In the sense it is straightforward. You connect, you can say in the sense you actually like take a serial manipulator. Okay, so you take a motor and you fix the rotational speed omega 1 and omega 2. So in the sense r theta 1 dot, r theta 2 dot. So you fix it, and L1 and L2 are known. So you are trying to find out what is x dot and y dot, right? So in that sense, what this is actually like straightforward. So which is we call forward, so differential kinematics. So this is what forward differential kinematics. What that means? So you have actually like q1 or q dots are actually like known, and j of q is actually like known, or you are trying to find out what is mu dot. You are trying to go this. This is what you call forward differential kinematics. Okay. So now the other way around. So the mu dot is known, and you are trying to find out this. So then what you are trying to do, the j inverse of q. So this is what you call inverse differential kinematics. Okay. So now I hope you got idea. So it is very straightforward as what we have seen as forward kinematics and inverse kinematics. So here this is actually like joint space velocity, and this is the end effector, or you can say task space velocity, right? You are mapping two velocity space, and the mapping matrix is here is Jacobian matrix. So where you have q dot is known and you are trying to find out mu dot, that is forward differential kinematics. In the sense you have a motor and you are running, in the sense what you are trying to see, if you are doing in a numerical, so you are trying to simulating the system. If it is actually like in the other way around, in the real, it is actually like analyzing the system. Okay. So the other thing is you know this and you are trying to find out this, in the sense you want to follow some end effector velocity profile and see that what your joint space velocity vector. So in the sense you are trying to actually like control, okay, but in velocity level, but without any feedback. So it is actually like open loop. Okay, in the sense it is actually like a feed forward. So that is what you can say, it is actually like inverse differential kinematics. So that is what we are actually like trying to see. I hope you can actually like see. So this is the forward differential kinematics, where this equivalent to simulating or analyzing the manipulator in velocity level, whereas the inverse differential kinematics you can easily recall, this is JQ inverse. So in the sense it is actually like if it is a square matrix, if it is a non-square matrix you would be using a pseudo inverse, okay, which we have written as J plus. So what this is equivalent? This is equivalent to controlling the manipulator in velocity level. However, it is in a open loop control scheme, in the sense it is a feed forward control. You please recall that. So it is a feed forward open loop. So now we will actually like see this J, okay. So this J of Q is actually like having m cross n, right. So now if m equal to n, then that is actually like giving a square, okay, where the determinant of J is actually like non-zero, okay. So then you can see that the determinant is non-zero, then the J of, so Q inverse is exist, right. But if it is actually like M is greater than N or M is less than N, then how you will solve it. So for that we will take Moore-Penrose pseudo inverse. So what that, this is actually like depend, if it is a square matrix it would be having equal linearly independent columns and rows, in the sense M equal to N, you can easily use the J of you can say JQ inverse is actually like simple adjoint of A divided by J, you can say determinant, provided the determinant is non-zero. But if M is actually like greater than N, in the sense, so you have actually like only 4 axes, but you have actually like spatial, in the sense 6D of system but 4 axes, okay. The sense the Q is actually like having only 4, okay, but the mu is having 6 cross 1. So if that is the case, what you have actually like 6 equations but 4 unknowns, it is actually like over specified. Then what you can do, you can actually like do the left inverse. So this is the left inverse, where we have a square matrix J transpose J or J into J transpose, right. So we take J transpose in J and take inverse and multiply with the J transpose. So this is what you call left inverse. So provided this determinant is actually like non-zero, okay. So why it is called left inverse? So this inverse what you are taking, if you are actually like multiply prefix or pre-multiply, that will give identity, and A this will not give identity matrix, okay. So that is the idea. So this will not give identity matrix, okay. So then you can see what is the other way around. So the other way around is actually like if M is actually like less than N, in the sense, so it is actually like for example 6 is the mu vector, but your N is actually like more than 7 axes, okay. For example it is 7 axes, in the sense Q is actually like N cross 1, right, that is 7 axes. In the sense this is actually like having 6 equation but 7 unknowns, in the sense it is actually like underspecified, you have multiple solutions possible. So in that case what you can do, you can actually like take the right inverse, so where you take J transpose inverse. So in this case, so what right inverse, so A plus equal to I, but A plus A is non equal to I, okay. So that is what we are actually like saying it. So you can see. So the other thing is actually like how this has come. So for that we are actually like taking a case 1 where actually like M is greater than N. So this can be solved with the least square method. In this case the situation is over specified. What the case? So you have mu dot, which is actually like J of Q into, so Q dot, this I am assuming as a 0. So mu dot minus J of Q, so Q dot is 0, okay. So this is what I wanted, but this is not possible, okay. But what I am trying to see, this 0 is not obtainable, but close to 0, or what is the minimum I can get it. So if that is the case, I can take a norm, second norm. So that second norm I can write it in this form. So now if this is minimum, what one can see, the dou L by dou Q dot supposed to be 0, provided the dou squared L by dou Q dot should be greater than 0, right. So that is what supposed to be known, right. So in that sense what one can see, you can actually like do the first the partial derivative. So in this case what would be the partial derivative? So this would be retained and this can be taken. So now you can see this. So in this case if you substitute equal 0, so don't say that this is non-zero, you pre-multiply everything. So then what you will get, so you multiply that, so you multiply this, you will get it. So now you rewrite this equation, you in the sense you take transpose throughout, so you will get this, okay. So now this is the rewriting equation and taking a transpose, you will get this, right. So now it is actually like very easy. So in the sense you take a transpose, this come, so now you wanted Q dot, so then this whole matrix actually like take inverse and multiply with this, so this give the left inverse, right. So in this case this is actually like over specified and it will give actually like theoretically no solution, but it will give come closer to the actual solution. That is what we have actually like say this is the pseudo inverse provided this determinant is non-zero, right. We will take the next case. So, the next case is actually like underspecified where m is actually like less than n. In this case actually like this is 6 and this is actually like 7. So, in the sense it is actually like underspecified. You can use a minimum norm method with the constraint optimization. So, what that means? So, the q dot would be exist, but multiple solution. So, you minimize the q dot, okay. So, in the sense you take 2 norm provided the mu dot minus j of q into q dot equal to 0. This is your constraint and you are trying to minimize this. So, that is what we are actually like doing it. So, minimizing this with the help of this constraint equation. So, then you can see the Lagrangian multiplier will come into a picture. Your optimization function or objective function would be not only this constraint also will come. Now, there is a 2 variables. So, dou L by dou q dot also like 0 and dou L by dou lambda also would be 0, right. So, 2 equation, 2 unknowns, we can actually like solve the unknowns. So, first I can actually like take the partial differentiation and rewrite this into one of the meaningful. So, what I can write? I can write lambda in the form of q dot, then that I can substitute here, then I can find the lambda in the order of mu dot. So, that is what first I take it this. So, the q dot I have written in the lambda form, that I substitute into the second equation, right. So, the second equation I substitute here, I substitute that. So, this will give. So, now I rewrite this where the lambda would be obtained in the form of mu dot. So, that is actually like obtained. So, now this I substitute into the previous equation, okay. So, what that equation? This equation if I substitute lambda, so this 2 and 2 will go. So, you can see this is look like a right inverse, right. So, that is what you can see. So, provided what you can see, so this determinant is non-zero, right. So, that is what we have actually like written. So, now what we have done? We have actually like taken left inverse and right inverse. So, and everything is actually like done and we have actually like seen. In the other way around, this class we have talked about differential kinematics. In that we have seen forward differential kinematics and inverse differential kinematics, where the inverse differential kinematics j of q inverse is coming. If the j is actually like a rectangular matrix, so you have to use the pseudo inverse, and in this class we have seen what is the pseudo inverse form we can use it. In the sense Moore Penrose we have used, and the detail why it is left inverse and right inverse we have explained. So, in fact, this detailed explanation is available in one of our previous conducted NPTEL course. So, I probably provide the link in the handout. You can go through in detail and then you can come back. Okay. So, with that I am closing this particular session, and the next lecture we would be seeing about velocity propagation. So, velocity would be propagate one joint to another joint, how it would be propagate from here to here. So, that we would be seeing. So, based on that we can actually like end up with final you call mu dot in the order of j of q into q dot, and one joint to another joint in velocity relation also we will be obtaining. So, that is what the next lecture. Until then, see you, bye, take care.